Okay, so good morning and welcome all of you again to this second day of the Tony 80 meeting. And before we get on to the talks, I would just like to say a couple of sentences paying my personal tribute to Sir Leggett. Well, while I just completed my PhD afterwards, I got interested in the subject of foundations of quantum mechanics. And in those days, that were early 90s, one had to only look to find, a series of very important seminal contributions by Professor Leggett. So I could mention just one or two. Of course, everybody is aware of his contributions on macroscopic reality. There was this Leggett work on temporal correlations that was so inspiring for all of us. And the whole idea of, the macroscopic limit of quantum mechanics inspired a generation of people at that time. And since then, of course, there were other contributions. I must mention his crypto non-local model that came slightly afterwards. And he was also a very, keen visitor to Calcutta. He had made a number of visits. And the last time I remember when I and Dipankar organized the conference, 75 years on quantum entanglement in 2011, he stayed there for a number of days and he inspired our colleagues, students. And since then, the whole field of quantum information nowadays got a major fillip inspired by the seminal works of Professor Leggett. Well, we should start the session today. And I'm very pleased to introduce Professor Spenta Wadia. Of course, he needs no introduction here. And he's going to speak about the Sachdev-Ye-Kitaev toy model of black hole physics in 2 dimensions. Thank you very much.
Thank you.
I'll just make a signal after 25 minutes.
Okay. Depends on your reference frame. Okay, thank you very much. And thank you for the invitation. I accepted the invitation almost instantaneously, but when I looked at the program, I was a bit intimidated by the fact that I'm the only string theorist actually in this meeting. But then I remembered that Tony Leggett also does not dislike string theories. Here he's between Edward Witten and Natty Zyberg. This is a photograph of the Solvay conference 2011, and congratulations, Tony, for your great 80 years, and wish you all the best in the future. Yeah. So let me begin my talk with very important equations of physics. These are Einstein's equations of general relativity. I'm not going to go into anything to explain anything over here, except to make the observation that this constant in front over here is extremely tiny, and this is the reason why gravity is so rigid and it's so difficult to observe gravitational waves. If I wave my hand, you don't feel anything, right? So this is the reason for it. Okay, so Einstein's equations have very important solutions with a long history. There's a black hole solution, which I will discuss briefly. There's the very important expanding and accelerating space-time solution, and of course gravitational waves, which were discovered a couple of years ago. And so general relativity is an experimentally verified framework to discuss black holes, cosmology, and gravitational waves. Okay, so this is a cartoon of a black hole, and these are the pioneers, and you can see Professor Chandrasekhar over here in his office with the pile of books, which is the Principia Mathematica of Isaac Newton. And here is a cartoon of a black hole. Basically, it divides space-time into inside and outside, or maybe better to say the inside is a forward, because if you have a particle over here, just beyond the horizon, when it comes over here, it'll just go in and disappear. Hopefully this works. I think this may not work. Oh no. It came out. I agree with you. Beyond the singularity, you mean. All right. Okay, so this object has amazing properties, and this is the Hawking's claim to fame. So in quantum mechanics, black holes are hot due to the presence of a horizon. I, in this talk, cannot really explain to you anything except these type of statements and give you some flavor of what's going on. So Hawking famously calculated this fundamental formula of the temperature of a black hole, and notice it's a quantum mechanical formula because it's proportional to Planck's constant. And in fact, I think this formula is now engraved on the grave of Hawking in England, UK. So anyway, these are some values over here to give you some idea that if you have a black hole of the size of a sun, whose event horizon is approximately 3 kilometers, then the temperature is abysmally low. It's 10 to the minus 7 Kelvin. If you have a black hole goes smaller and smaller, then the temperature increases. And in fact, if you have a black hole which is almost half the mass of the sun, then it's extremely hot. And hot bodies have energy in the form of heat, which is measured by a quantity called the entropy. And here you have this famous Bekenstein-Hawking formula. I think I forgot to put that famous 1/4 over here. Please forgive me. I mean, all the money is in that constant 1/4. Okay, so as I said, that if you have a black hole of the mass of the sun, which is something like 10 to the 33 grams, and you compress it into a radius of horizon which is 3 kilometers, then the entropy, the very elementary calculation tells you that the entropy is 10 to the power 76, and the number of states of such a theory is exponential of that large number. So you're dealing with a very, very large system. Okay, now, so that's for the static properties of the black hole. Now, if you have a hot body, it obviously radiates by interactions. And the important thing about a black hole is that it forms in various waves. Various ways. Whichever way you form a black hole, it settles down to the same object, actually. It's featureless, and it evaporates in the same way. All black holes evaporate in the same way, leading to information loss. And so, therefore, there is no memory of the way the initial state was constructed. Now, there are very beautiful theorems of general relativity which led to the idea, these are the area theorems, that so if the entropy is proportional to the area of the horizon, the idea that the entropy is proportional to the area of the horizon is very strongly supported by the area theorems of general relativity, which are very rigorously proved. And this is a very, very beautiful long story, but just no time for it all. Okay. All right, so you have a thermodynamic object, and there is information loss. There is information loss because a pure state went into something which is not a pure state, but something which is described finally by a thermal density matrix. So there is obvious conflict with the laws of quantum mechanics, and this is the paradox. Now, this paradox, which is called the information loss paradox of black holes, which was raised by Hawking already in 1974, can be understood because, if a piece of wood burns over, actually, you don't say there is a conflict with quantum mechanics. You say that there is a statistical description of this problem, and that description is basically due to Boltzmann. This is Boltzmann's equation. In fact, this equation is due to Max Planck, but it's called Boltzmann's equation. And we will be able to understand information loss if we can show that the Bekenstein-Hawking formula for the entropy can be understood as Boltzmann's formula. One great equation equal to another great equation. And the answer is yes. The answer is yes, and it's yes for a very, very deep reason. And this is perhaps one of the takeaways from this talk, is that the degrees of freedom of quantum gravity of the gravitational field are not only gravitons, but other objects which are called brains. That's the takeaway which I want you to, that the degrees of freedom of the gravitational field are brains. These are solitonic excitations, and these solitonic excitations interact very much like elementary particles interact by the exchange of gluons. Here they interact by the exchange of open strings, And they are sort of analogous to the molecules of water which are underlying the smooth surface fluid actually. So we want to discover what is below this continuum called the gravitational field. And these are the degrees of freedom. This is a hypothesis which is borne out in toy models, but let's go ahead very quickly. So this is important because these gentlemen in 1996 provided the first concrete evidence in a calculable model. You see, it is important to be able to compute things precisely, that black hole space-time is a sort of hydrodynamic description of more basic underlying constituents. They established that Boltzmann is equal to Bekenstein-Hawking in a toy model of supersymmetric black holes. You may criticize, oh, wow, supersymmetry, our physical black holes are not supersymmetric. Never mind. But black hole is a black hole, and in these models, they could, long ago, establish this very beautiful fact, fundamental fact. And then once this model was given, one could compute Hawking radiation in black hole thermodynamics, very much like in statistical mechanics, actually. Okay, so now comes the turning point, that these ideas of brains and interacting brains and their bound states being understood as black hole spacetimes all lack the certain basic framework. Actually, a basic framework means what is the precise definition of quantum gravity. And this is due to Juan Maldacena. And so I come to this holographic principle. These animations are borrowed from Juan, but they are not doing well in this particular software I'm using. So all these are particles on the boundary of a space-time which has gravity inside. So the basic point is, the basic conjecture is that anything that happens in gravity can be coded in a hologram on the boundary, and the hologram is described by a conventional quantum field theory, which we know how to work with. Okay? Now, the second point is that if there is a black hole in the interior of space-time, then it just leads to the fact that this quantum field theory or this many particle system on the boundary essentially is hot. So black holes correspond to hot quantum field theories. Okay? So these are two very, very important points of view, and this point of view, this particular idea is actually due to Edward Witten. Okay. So this subject has been sort of, worked on intensely for, more than 20 years, and a lot is known actually, but we are still very far, and let me tell you why. Okay, so now, now that you have a very precise formulation of quantum gravity. Now believe me, you have it actually, okay? You have it. In terms of a quantum field theory in which you can compute, hopefully, then we can ask many important questions. Like, what are the internal degrees of freedom of a black hole as perceived from the viewpoint of the theory on the boundary? Then what about wormhole solutions and their relationship to the information puzzle? Can one study black hole formation and calculate the Chaos exponent? Can be done in toy models. Well, this is a slightly older slide to appear. It has appeared. So this is what I will briefly mention towards the end of this talk. Okay, so now let me just pose for you fundamental problems of science, which should interest anybody. Because we have this precise holographic formulation of quantum gravity, here are a few questions which we need to answer. What are the fundamental degrees of freedom of quantum gravity? What are the degrees of freedom behind the horizon? Can one understand, calculate formation and evaporation of black holes? These are complex many-body problems. Can one resolve the curvature singularity that is beyond the horizon of a black hole? Can one study toy models of cosmology within ADS-CFT. This is an impendingly important fundamental problem that we have very little handle on, really. Okay, so these are important questions, and in order to answer these questions, one will need to solve these boundary theories. Now, these boundary theories, let's say for 4-dimensional, for 5-dimensional quantum gravity, is a gauge theory in 4 dimensions. For 4-dimensional quantum gravity, it is some other type of gauge theory in 3 dimensions. For quantum gravity in 3 dimensions, it's some superconformal field theory in 2 dimensions, etc., etc. None of these theories we can really solve in the large N limit, even in the large N limit, even at strong coupling. So their service, the service of the ADS-CFT correspondence for quantum gravity is as of now been very limited. I mean, we have learned a lot of things, but the real problem is still pending to be solved. Because these theories, these quantum field theories, are very hard to solve. You cannot put these on a computer either so easily because they are supersymmetric. So that's where also the problem is. Otherwise, you can just put it on a machine and let's see what the outcome is. But we can't do that. Okay. Now, let me change topic. This is the real talk, actually. All this was a sort of a background to build up to why we are doing things, simple things in 2 dimensions. Otherwise, you'll think I'm a loony actually working in 2-dimensional field theory. So, as I said, the black hole horizon basically tells you that there are enormous degrees of freedom that constitute a black hole. So, for example, many years ago, 't Hooft had this very beautiful idea that if you take the horizon area and divide it by the Planck area is something like 10 to the minus 33 centimeters square. So it's, very tiny. Then, you may have this idea that there is 1 qubit degree of freedom per Planck area. Okay? So these are very suggestive things, very qualitative but very suggestive. Now, somebody thought of making a model of it in which you can do a calculation. And this is the SYK model. So the SY invented this model about 2 decades ago in order to understand the properties of condensed matter systems which have no quasi-particles. So that's the Sachdev-Ye-Kitaev part, actually. It was formulated in a very different way. So a couple of years ago, Alexei Kitaev reformulated this problem with this idea of qubits of information interacting, what do they give you, and wrote down this very beautiful model as a simple model of quantum holography. So here is a problem with real fermions, n of them. There is a Hamiltonian with a random coupling with the J square is, oh, I'm so sorry, I forgot to put a capital J square here, excuse me. So that's the coupling constant of this model. Okay, so it's a Gaussian distributed random disorder, and these are basically Dirac gamma matrices in higher dimensions. And so this is the qubit model. That's the SYK model, one way of looking at it. Now I'll tell you the solution of the SYK model at large n at strong coupling. This is a very long story, but what is happening here is that Kitaev, preceded by Parcollet and Georges many years ago, Antoine Georges and Sachdev and E, discovered that there is a large emergent symmetry of time reparameterization at this infrared fixed point. Okay, so this is the symmetry. This is an arbitrary positive derivative function. It's called diff R1 in mathematics language. If you're on a circle, it is diff S1. The 2-point function of such a theory essentially has a very specific exponent. This goes as 1 upon 4 because there were 4 fermions. If there were 6 fermions, it would be 1 upon 6. So this is your, this is the space of symmetries. But this space of symmetries, these symmetries broken to SL2R by this solution. So there is a spontaneous breaking of SL2R symmetry. And therefore, the low energy dynamics you expect should be on this coset of diff R1 mod SL2R. This is very much like doing pion physics in particle physics, or Goldstone boson physics, wherever. All right. And then, what is the effective action of these low energy modes? This is the famous Schwarzian action. This is the Schwarzian. It's a mathematical object with beautiful properties, including the fact that if F is an SL2R transformation, then this object is identically zero. And this was the motivation to, in fact, phenomenologically write down this action over here. So this is very easy to do. The hard part is to compute this number. That was done by Maldacena Stanford in an amazing paper. Kitaev couldn't do it, but they were able to do this. And anyway, for us, it's not important, all this. Now, the important point I want to make is that finite temperature in this type of model can be understood in terms of this type of large conformal transformation, okay? So you see, it takes the line to the circle, in fact, to half circle. And once you understand this, then you can plug this solution over here and compute the free energy of this system, and the specific heat of this system, therefore, grows linearly as the temperature, as is also known by doing numerical work, etc., etc. All right. This is what it is. Now, what is the reason why this model is important? What was Kitaev after? He was after proving the fact that this model actually saturates what is called the chaos exponent. What does that mean? Take this type of anti-commutator, okay? So it is what is called the out-of-time ordered commutator. It is not the ones that you usually use in quantum field theory. And you can compute it actually, either numerically or analytically. And what you find is this very beautiful answer. It grows as J, which is large and strong, and is also suppressed by N, which is the number of degrees of freedom, and it has this shape. This is a ramp and this is a plateau. Both of these are extremely significant objects, which I think theories of black holes would like to explain in the future, but I will not dwell on that, except to tell you that the SYK model, just like black holes, saturates what is called the chaos bound. This is the bound. No Lyapunov exponent in a unitary field theory or a many-body system can actually exceed this value. This is h bar. Sorry, I forgot to put that bar over here. Okay, so this is the reason why the model was, to begin with, important. Now, you have a model like this. What is the dual geometry? The dual geometry turns out to be SL2R because of that subgroup of diffeomorphisms which we used to set up the dynamics of the Nambu-Goldstone mesons. Okay, so the dual geometry turns out to be the upper half Poincare plane, very well studied, great mathematical object. I will not dwell more on it. The theories actually that produce this type of geometry are two theories of gravity in two dimensions. One is what is called Polical Gravity, which arises as the coadjoint orbit of this diff 1 mod SL2R, and the other one is what is called the Jakob-Teitelbaum theory. Maybe these are just words for you, but believe me, these are two theories of quantum gravity in two dimensions which are asymptotically ADS2, but both of them essentially have only degrees of freedom at the boundary. And once again, those degrees of freedom are exactly the same like in the SYK model. And so for large N strong coupling, the low energy dynamics of SYK is dual to a two-dimensional theory of gravity. Okay, so therefore we can use SYK to study properties of black holes in two dimensions. Now, what are black holes in two dimensions? You might wonder about that. This is what it is. So, black holes in two dimensions don't have singularities. They don't have curvature singularities, but they have horizons. And we are interested in the dynamics of horizons, how horizons are created, how horizons are done away with. Okay, so that's what the rest of this talk is about. Can I have 5 more minutes, Chairman, Chairperson?
Depends on the organizers. I'll find with you.
Depends on the organizers. Where are they? Okay, all right.
You have 7 minutes and all.
Okay, okay, good. All right. Yes. Yes, of course. Of course. There'll be too many questions, I think. But I'll take care of it. Okay, so now we have these maps of the boundary. These are functions of a certain type, and they lead to two metrics, basically. Okay, this metric is the Euclidean metric, and this is the Lorentzian continuation of it. You see the appearance of the Schwarzian in the metric. It's really nice, this formula. So there's a map between the boundary degrees of freedom and the metrics. So it says basically that the large and low energy solution of the SYK model corresponds to a nearly to ADS2 metric, and these are the formulas for the metrics. Now you can just compute. So if you knew these functions, you can compute these metrics. And that is the point I want to make in the rest of the talk. All right, so here, let's look at this metric in a very simple formula for f of tau. This is the tangent function which I mentioned before. And if you compute, you essentially get a geometry, which is a cigar type of geometry, which is, you know, a real characterization of a Euclidean black hole, that if you take the time circle over here and shift it here, then the radius of the time circle vanishes when this object vanishes over here. Okay, so this is a black hole geometry. Okay, now the Lorentzian continuation, this geometry essentially has a horizon, because this object, the same object, vanishes. And you have a geometry like that. This is basically some massaging of the Poincare upper half plane. This is the horizon, and these are the trajectories of these particles which are described by f of t. Okay, all right, so this is sort of general understanding of the SYK model and its solution in the large n low energy limit. And it tells you that now I can use this model to discuss basic properties of black holes. So now we come to a very important, this is the important part of the talk, that what are the microstates of this theory? So the microstates of the SYK model essentially are spins. Okay, I mean, these are Majorana fermions, gamma matrices, so I can construct the spin operators, and I have a Hilbert space of dimension 2 to the power of n upon 2. Any state in this theory can be discussed in terms of up and down, up and down, up and down, etc., etc. Okay, and you compute the energy of the states. You can do this calculation even analytically, and you can conclude it's nearly zero. So it is very, very much higher than the true ground state energy, which is given by minus n, that is very, very negative, large. Okay, so this is the Hilbert space. But now you want to do a low energy projection, define a new state like this for very large values of L, which is beta upon 2. This state actually is almost a thermal state. So this is a typical pure state which acts as a thermal state. But it acts as a thermal state only for a class of operators which are invariant under what is called this flip symmetry of the SYK model. Okay, so this is a symmetry in which the even fermions flip sign and the odd fermions don't. And if you have an operator which is invariant under this, then this expectation value is the thermal average. If the operators violate this flip symmetry, then they are not thermalized. Now, there's a big story over here, but I just want to cut it short and tell you that this state, which acts like a thermal state, can be unscrambled. You know, you can now unscramble it by adding a very precisely tuned perturbing Hamiltonian over here. And this perturbing Hamiltonian is nothing but the sum of these spin operators, but with an eigenvalue Sk over here, which exactly matches this set of eigenvalues. So this is the so-called state-dependent operator, which was introduced by Raju and Papadodimas. So, okay, Raju is a professor at the ICTS. Okay, so you do this perturbation, and what it does is that it adds on to the low energy effective action. So you have a new dynamics of this reparameterization functions, and you can show that if you look at the equations of motion over here, the correlation functions are no longer thermal. I mean, you know, these are calculations you can do exactly, and you can actually see all this happening. So this new state, as it moves forward in time, does not evaluate thermal averages. Okay? So you have unscrambled the black hole by this type of perturbation. It sees where the microscopic theory came from, actually. Okay, so this is just in the dual geometry, what is happening is that this horizon has disappeared in this new dynamics. Okay? Now, what did we do? We took this model, we took this state, you know, in which the horizon has disappeared, and we asked ourselves, can we recreate the horizon and study the dynamics of the creation of this horizon of black hole? And indeed, it is possible to do it. It is possible to do it in, you know, you can actually solve everything in these type of models. So it's very nice. You can do it, and the new exact solution for this function f of t implies, I mean, that's a long calculation, that this new state, which is evolved by this new Hamiltonian, you know, with a parameter epsilon 2, which is less than the previous one, is a thermal state, and with a new temperature. So you have actually seen the birth of a black hole. Now, these geometries can be analyzed as a critical geometry involved in this problem, but I will not detail it over here because of lack of time. The only one point I will make is that if you compute the 2-point correlation functions in this problem, when you do the second quench, that is when you pump energy into the black hole, into the system, not in the black hole, but into this system which has no horizon, then these correlation functions develop a certain kink, a singularity. You know, this type of things have been studied in many body physics, and there is already a beautiful connection with black hole formation, non-analyticity of the 2-point correlation function, thermalization. All these things are involved in these simple models. Okay, so here is the last slide. So in summary, I would like to say that a quantitative understanding of the theoretical problems posed by the existence of black holes in nature and general relativity can reveal insights into quantum gravity, which are also important for a theory of cosmology. As we saw, this problem is at the confluence of many disciplines: quantum field theory, general relativity, condensed matter physics, statistical mechanics, mathematics, and information theory. I skipped over a lot of this stuff in this co-ed joint orbit business, but it's all there. So that's fantastic, no? I mean, so many communities, their methods and ideas and their imagination being used to solve this incredibly difficult problem. And coming down and lowering our, you feel really humble in front of this type of problem, that we have solved the problem of black hole creation in a very simple context in the large N limit. However, the important problem would be to discover the microstates. You see, if you take large N limit, it's nice, you can solve it, but you lose a lot. You lose the microstates, actually, the microstates in the gravity theory. The important problem would be to discover the microstates, which we have in the SYK model, and the discrete spectrum of general relativity once again in the bulk. This is a fundamental question, how to go about doing that. And Steve Schenker has conjectured that the spectrum of black holes in general will be akin to the spectrum of random matrix theory, and has the statistics of the spectra of random matrix theory. It has its rigidity and its short-range repulsions. All those properties would be part of the discretium, which describes the energy levels of a real quantum black hole. And with those few words, thank you very much for your patience. And yeah.
Thank you very much for finishing in time.
Oh, thanks.
And yeah, we will actually take the 5 minutes break now.
Okay, all right.
But I'm sure there must be some questions or comments.
I have an elementary confusion.
Yes, Haridas. Those are the problems.
Representing thermal states as a pure state.
Exactly, but that
How
is.
can that be possible?
But that, well, firstly, this can be shown that those averages are the same as thermal averages, okay, for those operators. You can prove it. But this is a very ongoing big subject in statistical physics, condensed matter physics, this what is called eigenvalue, eigenstate thermalization, essentially talks about a typical state in the theory which can actually evaluate thermal correlators. It doesn't happen for every system. For example, systems in which there is localization, it doesn't happen, but otherwise it does happen. It doesn't happen in integrable models also.
Other questions?
So Spenta, in SYK model, so do you understand which feature is exactly what is responsible for saturating the Mandelstam amount? I mean, can I think of any other model which also does the same thing?
Yeah, this is a good question. I mean, I think the reason, the property, I think, of the SYK model that is responsible for the maximality of the chaos, I'll come to the other things, is the fact that it's an all-to-all interaction.
I see.
Okay, so wherever you have an all-to-all interaction in many other models also, like tensor models or complex SYK models, it always saturates the chaos bound.
But it has nothing to do with the lack of quasi-particles.
Not to my understanding. I mean, this is a difficult subject, but let me comment on the fact that there was this ramp and then there was a plateau. Now, this is what the plateau has to be there, because if you have discrete states, a discrete spectrum, then asymptotically, for example, there are lots of order parameters, or you take the absolute value of the partition function evaluated at complex time, and you see its asymptotic behavior. Because the spectrum is discrete, you will have a plateau. Okay, the ramp has to do with this exponential of t times lambda L, this Lyapunov thing, and so the answer. So I'll tell you what I think is the answer. If you have a system which is dual to gravity, to a black hole, then it will always have maximum Lyapunov exponent. It will always have a ramp. That's the answer. Yeah, that's the answer. Because gravity always has it. It's always there, actually. So this 2 pi upon beta is nothing but the Unruh factor that multiplies the time near the horizon of a black hole. That's the physics of the. You see, it's so simple there, but then that will come out that way. Yeah.
Sorry.
Yeah.
You introduced spins,
Yeah.
combining Majorana fermions, and then microstates. So are they emergent new degrees of freedom, and how do they organize?
Yeah, those are not emergent. They are just there. They are the ultraviolet degrees of freedom. They are just there in the spectrum.
But then you construct microstates out of them.
So those are the microstates of the SYK model. So what we did is we took a low energy projection, then we used this notorious large N limit, which we all like, but it has a problem, and we washed out all the features of those microstates. Because you take any microstate, any collection of spins, any of them, doesn't matter which one, there are so many choices, 2 to the power of n upon 2, all of those states thermalize, and they evaluate those thermal correlators, actually. The point is that in the dual theory, where is all this hidden? That we don't know. You see, the calculation of the dual theory which I did only has those long wavelength gross features which are embodied in this function f of tau. But I think we need to discover these states in the gravity theory. That's the problem. That's the problem. Yeah, that's a finite n problem. That's the difficulty.
Yeah, just a small clarification. First, you talked of unscrambling the thermal state, and finally, in the SYK model, in the large n limit, you recovered back the.
I mean, everything was done in SYK model.
Yeah, at the end. So,
yeah.
I mean, what happens to the information paradox then? If you have a thermal state, then.
No, I mean,
solution.
I mean, if you know how to construct these states which have all these gross properties, there is no paradox.
Okay, maybe we can.
Yeah.
There's another. Okay, very brief question.
Yeah.
I'm not sure this question could be asked in 2D, but in higher dimensions, if there's a single black hole in equilibrium, then that's supposed to be dual to a thermal state
Yes.
on the boundary.
Yes.
But what about black holes which is something like what you're looking at here, not in equilibrium, or alternatively, say pairs of black hole, one on this side of the universe and one on this side, and then maybe they come together and merge. Is there any insight into the dual picture corresponding to those processes?
No. See, so this is why I was saying that all this discussion was in the context of the ADS-CFT correspondence, where there is a boundary. So you have a black hole, it radiates, and the radiation just bounces back from the boundary, and the system is in equilibrium. So those systems I know how to handle. But the one you're talking about, for example, in asymptotically flat space-time, I don't know how to do it actually, really. This cannot be, this technology cannot be done.
I suppose we could do it in asymptotically ADS, but
Yes.
it wouldn't be the stable equilibrium black hole, but you could have two small black holes.
Yes.
Which
In
were
ADS,
separate in
are you talking about black holes in ADS space-time?
Yeah, couldn't you
Okay.
have that? Yeah,
Two black holes?
two black holes, yeah. Yeah.
Yes. And what is the question then?
And then suppose they come together and merge.
Oh, yeah. So that's a very, yeah, okay. I think, so what you do is the following. So if you take global ADS to space-time, it has two boundaries,
Yeah.
right? And I can put a SYK model on one boundary and another SYK model on another boundary, and I can couple them. And that system has been analyzed beautifully by Maldacena and Chi, actually. And this is what, if you couple these systems in a very specific way, then you can have a traversable wormhole, which can communicate between these two boundaries.
Right.
And yeah, so this system can be handled, yes.
So you're saying two could be handled, but not three? Is that the story? Or well, okay.
Yeah, it's a very good question. I don't know the answer to this. Yeah.
Well, thank you very much once
Yeah,
again.
thank you.